to worry about the schedule for the final project presentations. There is no good way for assigning the names of students to the slots. So this is my initial assignment, but by all means feel invited to swap among each other, okay? I don't care whether this order will be completely destroyed afterwards, but I need to make sure that we have 4, 4, 4, 3, or 4 presentations, okay? So no more than 4 on any of these given 4 dates. Those are the 4 last lectures, and assume that indeed the first presentations have to be given on 5/29. I might decide that I want to do lecture number 17 myself, depending on how I progress with my material, right? And I have a certain objective for myself what I would like to talk about. But I'm pretty sure that I can be done nearly after lecture 16. So this would be lecture 17, 18, 19, 20. No more than 4 per those. But for example, if you wanted to move around or have 4 speakers here and then only 3 in the first one, fine with me. Just agree among each other, okay? Again, so what do I expect there for the talks? At the time of your presentation, you do not have to be done with the implementation, with your prototype, okay? So your presentation really should just be about your goal, what you would like to demonstrate, right, at the very end of the class, right? So the deadline for actually demonstrating your working project, or hopefully somewhat working project, is the same date for everyone. So here it's just you talking to your classmates about the literature that you are reading, that you have read, the essential ideas that are out there that have already been implemented, done by other people, and then your own cool ideas, what you would like to add, develop, try, compare, test, right, or develop completely new from scratch. There is no literature out there. No one ever had this idea before. You are the very first one. Fine with me too. Just convince the class that you are the very first one to do it. Okay? So it can be as researchy and as challenging and as exciting as you want it to be, the final project. So here it's just talking about what's the input to your project, right? Where do you start from? The question, the challenge, the data set. What's the goal? Where would you like to lift yourself, right? How far would you like to reach? What's the algorithmic objective? What kind of problem would you like to tackle? What would you like to have designed, implemented, or developed at the very end? And you should talk also about the ideas that underlie your implementation, right? The ideas that will go into your program. But again, at this time of the presentation, I do not expect anyone to have things already implemented, at least not implemented fully. Okay? But at this point, I would like for everyone to get going with doing at least the literature background, right? Big background study, going through the papers, blah, blah, blah. For many of you, looking at your proposals, for many of you, your talk will be about your research projects anyway, so this talk should not be too difficult. Okay? But again, it's very important that you know that you are the expert about the topic that you present, and only you understand that topic as well as you do. No one else in the class understands it, right, to that level. So you have to make sure that you present it in a way that all your buddies in class will understand it, right? You cannot talk, and after 3 or 4 minutes in your talk, you are so deep into your details that everyone is lost, okay? You can't do that. So you have to force yourself to present it to competent people, right? All graduate students, but you're the specialist in this particular area. Keep that in mind, right? Also, when I talk, I have to always force myself to talk at the level so that it's hopefully understandable, right, to a broad audience. Today I talk to you, tomorrow I talk to a different audience, so always, make sure that you keep in mind that you're talking to computer scientists, applied mathematicians, computational physicists, etc., right? And they use different languages, so whenever there is a specific language, domain-specific, try to lift that higher, right, to the next level so that's understandable to the person who is not in your discipline. As a computer scientist, try to talk to a physicist. As a physicist, try to talk to a mathematician, and so forth, right? So the language has to be this general scientific language that is understandable more broadly. So you will not impress your classmates if you talk at such a level of detail that you lose them after 5 minutes. No, you will impress your classmates if they are still excited after 20 minutes of your presentation. Okay? Yeah, Jennifer?
Should we have slides?
You can do whatever. Okay? I do not want to force you. Anyway, you can use PowerPoint. I mean, you can connect it over there, right? You can bring your laptop. You can give a PowerPoint presentation if that gives you more comfort, makes you more comfortable, by all means. But again, a lecture is 80 minutes, so we have 4 presentations. That makes 15 minutes for your own time. So I would like to see that maybe you have 15-minute talk time, and then there's 5 minutes of interaction between yourself and the rest of the class, so there's some interaction. So assume that you have about 15-minute presentation. That means no more than 15 slides if you use slides. Okay. So I see you can use overhead slides, you can use PowerPoint, or you can use, as I do when I lecture, the whiteboard. Or you can do it free speech, which requires a great deal of competence if you are able to do that. Again, keep it at a high level, right? Because your projects are very specific, right? They are very researchy already. They relate to your own focus of research, and be sure that you're the only one who understands that material at that level of detail. No one else in the class, even though you're all PhD students, right, will be able to follow you if you dive into the detail right away. You don't have to. Okie doke, that's that. And again, at the time of the presentation, I do not expect any demonstrations of preliminary implementations, preliminary prototypes, not necessary. Right? Everyone has the same deadline for that, namely, I guess, the day of lecture number 20. After that one, we have the demos for that. Okay, any questions about that? Okay, so again, presentation style, your own choice. Whatever medium you like best, choose that. And I guess the 2 obvious ones are whiteboard, blackboard, or PowerPoint. Okay, and everyone is invited to swap his or her time slot. Just keeping in mind that we only can have four speakers per lecture. All right, so last time we talked about this magic notation of barocentric coordinates and barocentric coordinate-based parametrization of triangular patches and all of that. And so I would like to go back to that because we will talk very soon about triangulation-based approximation. And I would like to essentially hit maybe 3 or 4 topics tonight. So topic number 1 is going back to this barocentric coordinate-based parametrization of triangles and simplices in general. Then I would like to talk about what is called curved elements. Most of these elements that you have seen so far in your lives are simple elements, namely they have flat or planar faces, right? So when you think of a tetrahedron or a tet, that thing is supposed to be having flat or linear planar faces, right? When you think of a cube or a hexahedron or hexahedral elements, you are tempted to think about these things as being elements with planar faces. But even with a hexahedron, it's already, the faces become very quickly bilinear faces, which are no longer flat. And so I will talk about creatures which are not consisting of flat faces at all. These creatures I talk about are really deformed creatures, okay? Curved creatures. So you can take a tetrahedron, and you can make the faces of the tetrahedron curved faces. You can take a cube, and you can make all the cube faces curved faces. So the entire solid undergoes the deformation. So I have to talk about that. And I want to talk a little bit about why that's important for numerical simulation, and why that's also important for approximation. And it's still an open area for research to some degree. After that, I want to talk about approximation of gradients. Right? This is what we want to do. We want to construct smooth approximations for scattered data. And if we only have the samples, the sample locations and the measurements as input, we always have to worry about good ways to estimate the derivatives, right? The slopes, the gradients for that data. I will talk about that for the 1D, 2D, and 3-dimensional case. And after that, I talk about a particular way to represent a function over a triangle when we know the 3 corner values and when we have estimated the 3 gradient values at the corners. Okay, so that's kind of like the outline, the direction for today. So, all right. So now I have to translate this outline into meaningful words, pictures, and hopefully also correct the formulas, right? So, triangular patches. Okay, so I started talking about that last time using the 1D case, but the most natural way to introduce this is to really talk about the triangle and the triangular patch. Again, one way to think about all of this is to think about a triangle in space and then deforming it, okay? Just curving it. You have a piece of metal here, and this is initially flat and planar, and then you just deform it. That's what's going on with all the symbols and all the formulas and all the pictures that I put on the board. So there is initially the domain space of the parametrization, and if we want to deform a triangle, well, we need a triangle to deform. And this triangle is typically referred to as a standard triangle, and it lives in 3 space. And it lives in a 3 space that has 3 axes, and they are called U1, U2, U3. And this particular triangle, if it's a standard triangle, ends at these base points, which are the points with values 1. And so this triangle is then characterized by the equation that the sum of these 3 variables or parameters adds to 1. And the way I've drawn it, since it's a finite, a limited area, the triangle area, the parameters are also all greater or equal than 0, right? For all ui, they are greater or equal than 0. So this is the parametrization that we deal with. Now we take this triangle and deform it. So deforming it, in our case, was in the context of constructing a triangular patch over sides that are initially given in the xy plane, having associated function values f. So we want to have a curved patch that lives here. And this curved patch, a projection of this curved creature living in 3 space, lives above a triangle. Okay. And so this is just one triangle of a gazillion triangles for which we have to do this construction over and over again, but it's always the same construction. And the corners I can locally always number corner 1, corner 2, corner 3. And then I used a strange notation where I said we have Bezier points, Bezier ordinates that live at these locations and span a so-called control mesh or control polygon in the specific case of a quadratic patch. So you get the idea. So there is this polytope, right, this piece of the polyhedron that is a control mesh that introduces or implies this underlying curved surface that lives underneath that control mesh. And I use a triple index because I use 3 coordinate axes for my parameter space. That's why the index is a triple one. And I call this guy control coefficient B2, 0, 0. I call this guy B0, 2, 0. I call this back guy B0, 0, 2. This one would be B0, 1, 1. This one would be B1, 0, 1. And this guy here would be coefficient B1, 1, 0. That's the indexing. I know that this is not a natural way to do indexing for something that is inherently two-dimensional, because we usually just think in terms of x and y. But because this triangular patch in this triangle lives over a parametrization that is itself a part of 3 space, embedded in 3 space, I need a triple index, and I need 3 parameter values. So then this representation of the patch in terms of a formula was this notation of a function. The function direction, the patch itself, the values depend on a triple argument, u1, u2, u3. And then it looks similar to a Bezier curve So there's a sum, and the weights or the coordinates are the coefficients b I1, I2, I3. And then there are the polynomials, the Bernstein polynomials in barycentric form. And they are, for this case of quadratics, 2 factorial divided by index 1 factorial times index 2 factorial times index 3 and the factorial of that times the first barycentric coordinate u1 to the power of I1 times u2 to the power of I2 times parameter 3 u3 to the power of I3. And so also I have to say that the indices I1 plus I2 plus I3 have to add to 2 the degree of that patch, quadratic, and all the indices have to be greater than 0. So 0 smaller equal I1, I2, I3 smaller equal 2. I can write this more compactly. I can just say this is the sum of certain coefficients with a multi-index b boldface I times, these are the Bernstein polynomials, bi of 2 of u as a vector. Okay? But don't be confused about that. You might want to forget this. You just think in terms of that. And so here is the norm of the index has to be the degree. Okay? I equals 2. But only if you want to think in this mathematical way. So again, we have a piece of metal, a triangular piece, which is the parametrization for a triangular patch that lives above the plane. And the way how we take this triangle, any parameter u1, u2, u3, and deform it to a point on this curved patch is given by this operator, by this function that operates on any parameter triple. And the way it does it, well, it computes this polynomial expression. That's it. Okay? So how do you get points on that surface? You just take any point in this triangle, right? This point here has a particular triple, u1, u2, u3. You plug the triple into this formula, you evaluate it, and you get, well, a function value. So this particular point is somewhere between u1 and u2, so between corner 1 and corner 3, and then a little bit inward, corner 1, corner 3, and inward. So it will be somewhere here, right? And the corresponding point on the patch will be there. Okay. Is the concept clear how that works? You have a triangle. A triangle loves to be defined in terms of barycentric coordinates. And then the curved parametric representation of this triangular patch is nothing but a deformation of a flat sheet of metal into a curved sheet of metal. Okay? And the way it is being deformed or curved is just this expression. So this is the specific case of n being 2, so that is a quadratic patch. Quadratic patch. The general case, of course, it can be an nth degree polynomial, right? It can have a bunch of wiggles, can be much more complicated. Okay. This is the way you represent a function over the plane to get a curved patch above it. And now I also talked about the issue of curved elements, right? Curved triangles in the plane, what is that? And curved elements, curved hexahedra. Okay? So these are just remarks, and some of you guys might be intrigued by that. This is the topic of curved elements. I think I should first motivate why that's important. Curved elements. Okay. When you do a numerical simulation of the flow field around an aircraft, is the aircraft consisting of planar pieces, of linear pieces? Not really, right? So those, when you look out of the window, it's curved stuff, right? So therefore, the simulation should not be based on just using linear pieces, but it should be using curved pieces. Kind of like makes sense intuitively. So either you use what is called adaptive mesh refinement technologies, where you start with some initial, very primitive, very basic mesh, And then you refine it further and further until it's a very high resolution, and you can indeed deal with constant or linear elements. Or you say, no, that's not good enough ever. I always want to use the curved nature of the wing to begin with, and I want to have an element that indeed has a curved face. And it smoothly touches, connects without a gap in between or without penetration, touches the wing perfectly, tangentially. Okay, that's where it comes from. So some numerical simulations, very expensive ones, are based on that. So motivation for these things. In order to represent the geometry precisely, or at higher levels of accuracy, and discontinuities where you have boundaries between different material types, you want to represent those locations exactly or with highest possible accuracy. Motivation to represent boundaries or geometry, and to represent the locus of discontinuities in fields. To represent discontinuities. Okay, so I'll just give you an example how this works. For example, for the simulation around the curved aircraft wing, right here you have your curved geometry, and assume that you really are given an analytical description of this geometry in terms of very high degree polynomials. So for computer graphics, you just sample this guy and use 1,000 points on it, and then you connect these points by straight line segments. That's good enough for rendering. But oftentimes for simulation at high levels of accuracy, it's not good enough, right? You actually want to use a curved piece. So, well, if you have a mesh around this wing to represent the space around the wing, you want to have elements that actually agree with the geometry precisely. You want to have, say, tetrahedral elements that look like this. They have two planar faces there, but where they actually touch the geometry of the wing, they should be precise. So this would be a tetrahedron in 3D, right? That where it touches the geometry of the wing must have a curved face there. So the other thing is this: there also might be a discontinuity, a shock wave, right, forming behind the wing. So there is an abrupt jump between the density of the field, the air pressure jumps abruptly. Again, once you have done an analysis and you know that there is a discontinuity in the field, in a field parameter, in a variable, I shouldn't draw it like a straight line. So there could be a shock wave, and the shock wave introduces a discontinuity. Again, in order to capture that, you would like to use elements that have curved faces. So this is the type 1 geometry you want to represent, and this is the type 2 geometry that you want to represent with your elements. So needed, not just desired, but really needed for high accuracy simulations. High accuracy simulations. Okay. So, all right. So here we have the triangle element, and this was the triangle element 2. Right? This is the triangle patch, curved in 3 space, living above the plane. Here we also have to worry about curved pieces, right? But they are of a different nature in a sense, so we have to talk about those. They are curved triangles in the plane, not above the plane. Curved triangles, curved triangles, and these are curved triangles in the plane. maybe a better word would be to call them deformed triangles. But so the parameter space for these guys is just like the parameter space I had on the board before. The domain is still this trivariate domain of 3 axes, u1, u2, u3. And I use my standard triangle. This is my parameter triangle. Goes up to the base points, 1, 1, 1. Now I take this triangle and I deform it. But not above the plane, but in the plane. So now I'm drawing something that really lives in the plane, the xy plane. So how do I take a standard triangle and deform it? Well, it will look like this. Okay. So this triangle is in the plane. It is not some kind of projection that I'm drawing here. It's really a deformed creature of that. So again, I have the control points. And this would be a quadratic patch again. This patch lives in the plane. It has control points like these, just like the guy before. This is a control mesh. The control mesh also lives in the plane. So what are the names of these points? Now these points are really points, xy points in the plane. So therefore I draw them as boldface, B2, 0, 0. The guy has 2 coordinates, right? There's an x component and a y component for this control point now. It's a point in the plane. x2, 0, 0, and a y2, 0, 0. This guy, this control point would be point B0, 2, 0. This point would be B0, 0, 2, and the others as before. Now, how do I take this parametrization or this standard triangle, the base triangle, and morph it into something that is curved in the plane? Well, it undergoes the same mapping, M. There is some kind of mapping ongoing there. And this mapping is now not this before it a function there, a function of parameters. Now it is space as a function of parameters. The space is the x space, right? I have now to say the point x of u, right? A point in 2 space depends on a parameter triple. So this is an x and a y component depending on u1, u2, u3, depending on u1, u2, u3, are formally the same as before. There was just this sum. There is just the sum of basic control points b, I1, I2, I3 times these guys are the Bernstein polynomials, right? As before, 2 factorial over I1 factorial, I2 factorial, and I3 factorial times u1 to the power of I1, u2 to the power of I2, u3 times the power of I3. Okay? And here the same thing, that this index I has to be of norm 2. Now what does this mean? That means if I take any point in this parameter space, then this point undergoes a transformation or a deformation or a morphing just like any other point in this triangle. And this point would become roughly that point, right? It's like stretching, compressing, right, and stretching something. But it's more complicated, right? The deformation is as complicated as these polynomials are complicated. So again, this was just n equals 2. We can make this higher. Now, if there is a deformed triangle, there's also a deformed tet. If there is a deformed tet, there's also a deformed hexahedron, right, and so forth. So now I just write this down. What this generalization is for the deformed tet or the curved tet. So the curved tetrahedra or deformed tetrahedra I can no longer draw the domain space because that's in 40. So I have to draw the deformed element in XYZ space. So there is a deformed element, a deformed tetrahedron. So this tetrahedron will have curved faces. So it will look like this. Right? This is a deformed tet. This is a projection of the deformed tet into this drawing plane. I do not want to draw its control net. That's too many control points, even for n equals 2, and everything gets occluded. But I want to draw the control net at least by alluding to it and drawing it on the front face. So these are the control points at the corners, right? And then the front face here of this deformed tet, if it was n equals 2, a quadratic curved tetrahedron, would have this control mesh part on its front. Okay. And then there are some other control points on the other four faces in a similar arrangement. So, and again, if you are pulling and pushing these control points of this tetrahedron in 3 space, this thing will deform, right? Just like you can deform a Coke can. Twisting and compressing it or expanding it. So now here I had to use a triple index. Now in this case I have to use a quadruple index, right? So this control point here will be a point B2, 0, 0, 0. This point will be B, 0, 2, 0, 0. This point will be B, 0, 0, 2, 0. And this guy will be control point B, 0, 0, 0, 2. And the other control points will have 2 ones, right? 2 ones as part of their index name. Say, I name this guy. This guy would be control point B. It is between the first and the fourth, so it is B1, 0, 0, 1. And that's the way the index works. They have to, all the indices, the 4 indices have to add to 2. And then you can get at most, now we get exactly 6 plus 3 plus 1, 10, right? There will be 10 in total. 10 control points. So this curved patch is a point in space, right? It's a point of a solid. So this is really a point x, depending on this quadruple. And it's a point in the solid, x, y, z. It's a point in space that depends on 4 variables. Barycentric coordinates, u1, u2, u3, u4. Up, and then the last one the same way, u1, u2, u3, and u4. And then the notation is the same. It's really that we now just have to deal with 4 indices and 4 arguments. So index 1, index 2, index 3, index 4, and then times the degree, 2 in this case, 2 factorial over, blah, 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 the product of the factorials of the indices, times u1 to power i1, u2 power i2, u3 to the power i3, times u4 to the power i4. Again, I want to motivate this again. Why do we need this? Why is this important? If you want to do a simulation of the flow field in this room, right? What is the horrible problem that you have to do? If you do a numerical simulation of the flow field in this room, the first step that anyone has to do with a simulation is to construct the so-called, usually, mesh or grid. Okay? But this room is filled with all kinds of ugly geometry. Huh? The ugly geometry is my jacket. The ugly geometry are the microphones. The ugly geometry are these lights and so forth. You have to represent that, right? I'm not even talking about our hair. It's even worse to represent. Okay, so no matter what, when you want to do a simulation as complicated as the flow field in this room, the first step you have to do is fill this room with a bunch of bricks. Can you fill this entire room between these objects with just bricks? No. You need curved creatures if you want to do it well. Right? Your room doesn't consist just of flat walls and flat tables and flat bodies. Right? It's just everything is curved and round. So, therefore, if you want to do a decomposition of this space and break it down between our bodies, between the tables, between the lights and our bodies, in the best possible way, you need to fill it with, well, perfect tetrahedra here and there and perfect cubes here and there. But when it comes to representing the geometry, the boundaries, then you need to do something else, right? And so that's why these things are important. And the objective is to have a method, and this is unsolved, to come up with a method that fills this empty space between these objects with a minimal number of optimally placed curved elements of lowest degree. Huh? That's the optimization problem. That would be great if people knew that, but it doesn't exist. Okay, the input to such a method would be the description of our jackets, our bodies, of our hair, of our cups, of our everything in this room. And then the output of that method would be the perfect grid or the perfect mesh. And the perfect mesh would be a minimal number of elements that have to be curved, at least in these areas where they touch curved pieces, but they should still be of relatively low degree, because high degree is expensive and wiggles around, has oscillations. Optimal placement of minimal number of elements that are curved, have to be curved in certain areas, but are curved with respect to a low polynomial degree. Okay, that would be great if that existed. This method doesn't exist, and that's why people do it in the most straightforward way. They just put one big brick in this room. One big block represents this entire space, and then they do clipping or trimming, right? Then they clip all the geometry out. How to do that? Well, they take the one big brick and then they cut it into 8 octants, right? 8 baby bricks. Then you refine it more and more. And in certain areas, the geometry is much more complicated, namely there where they have to cut out my body, right? So in order to conform to my body, you need to refine this mesh, which only consists of perfect cubes at smaller and smaller scales. You have to cut and cut and cut and cut, and you get a huge number of levels of refinement, sometimes up to 15 levels or 16 levels or 17 or 20 levels, okay? And in fact, in terms of the error, it's still not good enough, because the phenomenon is not a phenomenon that is based on cubes or bricks. The phenomenon is based on something that is curved. So that's why this is important. So now I talk about the curved bricks, the curved cubes. Okay, what are the curved hexahedra? I talked about the curved triangles and tetrahedra first, but now I also should talk about curved quads, quadrilaterals, right? Quads and hexahedra, or cubes, hexahedra. And just very briefly, it's a little bit more natural to think about these guys, because this is our typical way of looking at the world with orthogonal coordinate systems. So in the quad case, we just have a two-dimensional parameter space, U1 and U2, and we can think of a deformed quad as a unit square that is being deformed. So if this goes from 0 to 1, and this here, in the other direction, goes from 0 to 1, then this perfect square gets deformed in xy space into a curved quad, and the curved quad living really in this plane would look like this. Okay. And again, why do we need it? Well, this curved quad might have to conform to an aircraft wing, right? For example. So this thing is curved in the sense that if I were to draw isoparametric lines in the domain here of the unit square, then these parametric lines would become curved lines, right? So this region is now a deformed region. Huh? All right, what is this mapping that takes any point from here to a point in xy space? Well, that mapping has to be a mapping x that depends on u. So it is an x and y component, or an x and y coordinate function depending on u1 and u2. And again, this is now the more natural setting. This is now a tensor product. I can write this as a tensor product. And so this is, say, m equals 2 and n equals 2. That would be a bi-quadratic setting. So I say I goes from 0 to 2, and j goes from 0 to 2. And And this guy would have control points at the corners. And if it's a biquadratic, it would have additional control points like these. And the control mesh would somewhat look like this. Again, this lives in the plane. Okay, this is a mesh that lives in the plane. And so these control points are now B, I, j. So this guy here would be B, 0, 0. This one would be B, 2, 0. And this guy in the corner there is B, 2, 2. That's a more natural way of thinking about this indexing thing, right? This is a natural index. The triangle stuff and the barycentric stuff was a non-natural thinking. So, and this is BI of 2 of U1 times Bj of 2 of U2. And these are just the standard Bernstein polynomials of degree 2 as defined before. All right, so if I can take a unit square and deform it into a deformed square, then I can also take a unit cube and deform it and make it a deformed solid, right? Compressing it or stretching it or twisting it or making it self-penetrate, okay? Which we don't want, but you can do interesting things with that. So if there is a curved quad, there is a curved tetrahedron. So the curved tetrahedron has as its domain a triple parameter space U1, U2, U3. And I say I take a unit box. And so this is from 0 to 1. Y varies from 0 to 1. And Z varies between 0 and 1. Then I can take this box and deform it. And so it's the same mapping. And now that deformed cube in XYZ space would look maybe like this. Okay. I think you get the idea, right? So this is a cube in 3 space that is deformed. So then the control points are only, again, just like over there, I only want to show the part of the mesh on the front face. So these would be the corner control points. So this would be a tri-quadratic if I use this many control points, tri-quadratic. And on the front face, the mesh would look like this. Okay. It's a typical tensor product mesh for the surface, right? So the faces are surfaces, and then the solid is a solid. So this guy would be control point B2, 0, 0. And this guy would be control point B2, 2, 2. This guy here would be B, what is it? No, this guy is B0, 0, 0, okay? Lowest left front corner is 0, 0, 0, and the one furthest away is B2, 2, 2. So this guy would be B2, 0, 0. This guy here would be B, 0, 0, 2. That's how the index runs there. And so now I have to tell you what the mapping is there. How to take a unit cube and twist it around. And again, now it's a point in the solid, depending on a parameter tuple. So we have a point in space, XYZ, which is the result of deforming the U space, the parameter space, U1, U2, U3, U1, U2, U3. And then again, this is just a triple sum. It's a tensor product. Sum, sum, sum. I from 0 to 2 in this particular example, j from 0 to 2, and k from 0 to 2. And then we have the control points. They have 3 coordinates, x, y, z coordinates, b, i, j, k, times Bernstein polynomials I of 2 in U1 times Bernstein polynomials j, order degree 2, of U2 times Bernstein polynomials index k degree 2 of parameter 3. Okay. How do you get a point in that solid? Well, you take any triple U1, U2, U3, you plug it into that formula, well, and you get a point there. Right? Okay. So, for example, simulating the blood flow, right? Simulating the blood flow is extremely complicated, a phenomenon. Simulating the breathing process in our lungs is extremely complicated, a phenomenon. Nevertheless, when you think of blood flow, these things are probably mainly circular, right? The veins and arteries. Okay. So if you were to try to resolve the arteries and veins at high levels of accuracy, just using a bunch of cubes, you have to refine it many, many levels to get a good approximation of the circle. It's pretty bad. Or if you want to simulate airflow and how certain bad chemicals or bad particles are going down into our bronchi and alveoli and so forth, you have to resolve these things down, even though you know that most of the things have a perfect circular cross-section. So then you should use cylindrical pieces to begin with, right? And you only need one of a certain diameter, right? When you have a really big, fat main vein or artery to represent, it's a sort of a nearly perfect circular cross-section, and then it has the main axis. Represent that thing with a curved, cylindrical solid, period. And when the thing gets thinner and thinner and becomes its tree in our body, well, then go to thinner cylinders, right? But your simulation should be based on such an element. To represent such a cylindrical piece, this microphone thing, you only need one element, one, and not 20 levels of refined cubes, right? That's the thinking. So particularly when it comes to biological processes, for biological processes, the geometry becomes even more complicated. You want to use these things. For many manufactured or engineered pieces, the geometries are oftentimes indeed planar, right? Linear. All right, so far so good. Now we have to talk about gradients. Shoot.
I was just wondering, why not just use polar coordinates?
Yeah, you can do that too.
Okay. This is just another way.
Yeah. Since you're the biomedical engineer, so you do the simulations of the blood flow and then the hips and all of that, yeah. Of course. So let's see. What comes next? Should I talk about approximation of the gradients next? Yeah, I think that's a good logical sequence. So these were representations, right? This is notation, or these are formulas that we need to move forward. So this is background. Now we have to think about how to use this. Before we can think about how to use this, I also need to talk about the gradient estimation. These representations behind me on the board are the building blocks to represent geometry and to represent functions. Before we can do that and use this notation, we have to worry about approximating gradients from the data we are given. Again, when we measure something out there in nature, temperature, wind velocity, salinity in the ocean and whatnot, we just get one value, right? The concentration, the temperature, the density, the energy, something. And so we have to estimate the derivative information. So I talk about that next, and then we have everything that we need. Then we have, in the scalar data sense context, we have sites with gradient estimates, and then we have to triangulate things, right? We need to use triangulation to triangulate the sites, and then we can put curved triangular patches above those triangles, or we can fit barycentric coordinate-based simplicial pieces over each tetrahedron in space, ultimately. That's where we are going. So we have to talk about gradient estimation, or derivative estimation. Derivative/gradient estimation again. All right, let's do it for the 1D case. The 1D case, what are we given to begin with? We are given points or sites on the x-axis, and we have them in scattered arrangement, so arbitrary, anywhere. Okay. And particularly we have these here, side xi, xi plus 1, and xi minus 1. That's the logical ordering and indexing from left to right, from 0 to n. And we need to worry about good slopes, right? So we need a slope here, we need a slope here, we need a slope here, we need a slope there, we need a slope there. So how do we get the slopes? How do we estimate a good slope for xi? Tell me.
We can interpolate them with xi minus 1 and xi plus 1.
We interpolate them with?
If we can subtract the two of them and use the distance from xi to determine their weight in the gradient.
Okay, so you want to get something like this, right? That's what you want to interpolate, to get a gradient?
Yeah.
Okay. That's one way to do it, right? The other way to do it is to look at these three sticks and say, well, there is one good line that looks like that. That's a good line approximating those three sticks, and therefore the gradient behavior in the neighborhood of those three sticks. And then there are other ways. And there's always, I just forget about this irregular spacing, and I just use this text that says it's always 1/2 of right minus left value, right? Right? You just forget about the spacing. It's always right minus left divided by 2, right? No, it's wrong. So that is only true when the spacing is the same and the spacing is always 1 from one sample to the next. Then that formula is correct, otherwise it's wrong. So, all right, so let's do Jennifer's case first. So, first, we can do a local quadratic fit, right? Quadratic fit. And it really fits because it is interpolating locally. So locally, the situation is like this. You have an x, and you have your three sides of relevance here, and they have non-uniform spacing. This is xi, this is xi minus 1, xi plus 1. Again, different spacing. There are some sticks, function values, f direction, given with these guys. Some fi, some fi minus 1, and some fi plus 1. And now we want to compute this guy, right? And say, well, this guy will have a very well-defined slope there, and we will use that as the estimate there for slope. So this thing is a parabola, and if it's a parabola, it's a quadratic polynomial that depends on x. And if it's quadratic, it has three coefficients. It's an a plus bx plus a cx squared. So there are 3 degrees of freedom, a, b, c. We have 3 constraints for the parabola to pass through. So that's what we just write down. Constraints. We want the parabola, which has coefficients a, b, and c unknown, to interpolate the values fi minus 1, fi, and fi plus 1 when we plug the different sides in there. So when we plug the sides in there, well, we have to plug the sides into these x expressions. So it is 1 times a plus xi minus 1 times b plus xi minus 1 squared. The next one is 1 xi plus xi squared. The last one is a plus xi plus 1b plus c times xi plus 1 squared, right, equals last point. So we have a 3 by 3 problem. From this, you solve this thing, you obtain the triple, the coefficient triple ABC, right? And so now you can evaluate, of course, this quadratic polynomial once you know a, b, and c for the location in the middle, well, for the side of interest. So you can now say the derivative q prime at location xi is this guy evaluated at xi. So it is just a plus b xi plus c times xi squared. Well, since he wants the derivative, you have to differentiate that thing. No? If you differentiate it, it is b plus 2 times c xi. Right? You don't want the value there, you want the derivative there. So this differentiated with respect to x is b plus 2c x. No? And so you have this. And then you will just use this value, q prime, as the derivative there. You will just use this as fi prime. Boom. And now you do this plays this game all over the place, and you get nice derivative estimates. Now the other approach of doing it is you use a least squares linear approximation. It's not a fit, it's just an approximation. So what do you do there? Again, you look at the neighborhood of 3 points, 3 sides, 1, 2, and 3. Side, 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 xi minus 1, xi and xi plus 1, and value, value, value. And you want to get a definition of this least squares line, which looks like this. This is the best possible line that approximates in the best possible sense these function values. So this will be a line to approximate fi minus 1, fi, and fi plus 1. If it's a line, then it has an expression of the form line of x equals, well, a plus bx, a plus bx. And now we have this misery that we have 3 sides and 3 values, that we only have 2 degrees of freedom. That's why it becomes the least squares problem. So again, the setting up of this problem is as follows. Setting up